Good afternoon. Transmission lines. So the next point is solutions of homogeneous TE. So here are the equations which are given for that. In the previous lecture we have seen the secondary primary constants like resistance, inductance and conductance, and also the secondary constants like characteristic impedance, propagation constant, attenuation constant and phase constant. Also we have already seen the wavelength, velocity of propagation. So this slide shows the solution of homogeneous equation. Now here is the symmetrical network. The lump parameters Zin is Z0 of ZL plus Z0 tan gamma L. Then this diagram shows the characteristic impedance. So what is characteristic impedance? We know that the theory about the characteristic impedance, that any circuit which consists of series and shunt impedance has an input impedance. So for a transmission line, the input impedance depends on the type of the line, its length and the load connected at the output. So in simple language, the characteristic impedance is defined as an impedance which is looking into an infinite length of the line. So the characteristic impedance of line can be measured at its input when the line is terminated at the far end in an impedance which is equal to Z0. So the characteristic impedance of a line can be measured at its input when the line is terminated at the far end in an impedance which is equal to Z0. So if we consider an infinite length transmission line, then if the power is fed at input of this transmission line, then there will not be any reflection from the output end, and this is because the line is having infinite length. Since there are no reflections, there will not be any loss of the power. As there are no reflection, there will not be any loss of the power. That is, the maximum voltage and maximum current is obtained. So in this case, the characteristic impedance is defined as the ratio of voltage to current at any point along the line. What is characteristic impedance? Characteristic impedance is defined as it is the ratio of voltage to current at any point along the line. So mathematically, the characteristic impedance of an iterative circuit consisting of series and shunt element. So it is given by Z0 is equal to square root of Z by Y. Now what is Z? Z is series impedance per unit length, and what is Y? Y is shunt admittance per unit length. Now here block diagram is given. The identical symmetrical network, it consists of identical symmetrical network up to infinity long, and Z0 is the impedance, that is characteristic impedance. So the characteristic impedance, it is the ratio of positive traveling voltage wave to the current at any point. So here diagram for this is shown. It is the ratio of positive traveling voltage wave to the current which wave at any point on the line. Now here equation for the Z0, that is the characteristic impedance, is given. So Z is equal to R plus J omega L. R is resistance, L is inductance, Y is equal to G plus J omega C, and Z0 is equal to square root of Z by Y. So what is Z? Z is series impedance per unit length, Y is what? Shunt admittance per unit length, and gamma is square root of Z into Y. And what is gamma? Gamma is phase constant. Gamma is phase constant. lossless line R is equal to 0 equal to G. If the conductors of the line are perfect and dielectric medium separating them is lossless. Next is distortion. This is lossless line. Here is the equation for the distortionless line. So distortion is alpha and beta are the functions of the frequency. So alpha and beta are the functions of frequency. So phase velocity of each frequency component is also a frequency dependent. So here equation for the distortionless line is given. The transmission line characteristics. So here transmission line characteristics are given for general transmission line characteristics, for lossless and for distortionless. So what is distortions in the transmission line? There are different types of the distortions in transmission line, like a frequency distortion and phase distortion. So first is a frequency distortion. The different types So different types of distortions in the transmission lines are alpha is the function of frequency. Alpha is a function of frequency. Alpha is a function of frequency. So all the frequencies which are transmitted on the line are not attenuated equally. When complex signal containing many frequencies such as voice is applied at the sending end, then at the receiving end the different frequencies are attenuated by a different amount. So his received waveform is not same as that of the sending waveform, and it is known as frequency distortion. And it is known as frequency distortion. So this distortion is very serious and undesirable for audio, or we can say voice communication, but it does not affect the video signal too much extent, and it can be reduced by using equalizers at the line terminals. And the second distortion is the phase, or we can say delay distortion. So phase constant is beta. So beta is a function of frequency, and the velocity of propagation omega by beta is also function of the frequency. So all the frequencies which are applied at the input will not have the same time of transmission because of different P, with some delayed more than others. Thus, applied signal at the input will be different than that of the received signal at the output, and this phenomenon is called a delay, or we can say a phase distortion. And this distortion is less objectionable in voice or music transmission as out for music transmission, but it is highly undesirable and objectionable in the video transmission. So coaxial cable, or we can say a flat parallel tech cables, are used in the picture transmission of TV signal. Here equations for the input impedance is given. Now the next point is reflection coefficient. So the voltage reflection coefficient at any point on the line is equal to reflected voltage wave by incident wave. So the ratio of amplitude of reflection voltage or current wave to the incident voltage or current wave at the receiving end is called as reflection coefficient. Ratio of amplitude of the reflection voltage to incident voltage, we can say reflection current to incident current wave at the receiving end is called as reflection coefficient. So reflection coefficient is given by K. It is equal to reflected voltage at load divided by incident voltage at load, or we can say reflected current at load by incident current, reflected current by incident current at load. So if the line is terminated into characteristic impedance, that is ZR is equal to Z0, in the first diagram it is shown ZR is equal to Z0, then K becomes 0, that is reflection coefficient is 0 as there will not be any reflections. When it is open circuited, that is ZR is equal to infinity, then K is equal to 1 minus 1 by infinity divided by 1 plus 1 by infinity. So reflection is maximum here. And the third case, when ZR is equal to when the line is shorted, that is when ZR is 0, the first case is here, when ZR is 0, then K is minus 1 plus J0, reflection is maximum. So angle and magnitude of ZR and Z0 will determine the sign of K and hence the polarity of reflected wave. So the magnitude of K varies from 0 to 1 and its phase varies from 0 to 180 degree. Now here equation for the SWR and Zin is given. So this slide shows the summary of the equations of load impedance, reflection coefficient and SWR. Thank you.